All right, great. Hello, everybody. I'm glad that you could all make it today and listen to this talk. I definitely appreciate it. Also appreciate the great introduction. So as we heard, my name is Tyler Hernandez. I'm a fourth-year chemistry graduate student at Stanford University in Palo Alto, California. I work under the direction of Professor Mike McGee at the University of Colorado in Boulder. And I'm very excited to get the opportunity to share with you all today about what our group has been working on for the past few years. So as you can see from the title slide here, we're working to develop optically tunable dynamic windows. And you can see from the pictures here that this technology is able to go from a transparent to a color-neutral gray all the way to a dark black opaque state and return to its initial transparency. And they can do these rather quickly. So in addition to working on this very cool technology during my PhD studies, one of the great benefits about working in the McGee group is that I've had the opportunity to live in both the Bay Area and in Boulder, Colorado. And if none of you have ever been to Boulder, Colorado before, it's absolutely beautiful. And one thing it's known for is its flat irons. So this is the view outside of our lab right here, and you can see the beautiful mountains in the background. And you can be sure that anytime that we're working in lab, we always want to make sure that we can see these mountains out here. So we always keep these blinds open. But unfortunately, beautiful views always come with a cost, specifically when you have any type of direct sunlight. And I'm sure we're all well aware of when sunlight hits a computer screen and we get this terrible glare off the screen right here, making it really difficult to work. So what's the common solution to this day-old problem? We simply just shut the blinds. And of course, this solves our issue with unwanted glare. But the reason we're in Boulder, Colorado is to see the flat irons. And it's so unfortunate that existing technologies cause these views to be tarnished. So in the words of famous American stand-up comedian Dave Chappelle, modern problems require modern solutions. And the solution to this modern problem of unwanted glare and one's inability to both tune and control their comfort and environment, both thermally and optically, the solution to this problem, ladies and gentlemen, is electrochromic windows, commonly referred to as smart windows. So as you can see, we have many examples of pictures we have here. I'm sure many people here are very familiar with this technology, and one great thing about it is that there's two different advantages to smart window technology. There's both the energetic side, and there's also the aesthetic side. So on the energetic side, the ability to be able to dynamically control solar radiation would drastically improve the energy efficiency of buildings. Specifically in the United States alone, about 40% of the energy is consumed towards buildings. And it's estimated that the implementation of these smart windows would lead to about a 10 to 20% energy savings over static low-E coatings. In addition, on the aesthetic side, not only are these windows beautiful, but if you're able to both thermally and optically manage the interior of a building, this would lead to increased occupant comfort, which would also lead to increased employee productivity. And there was a great study done between View Glass and Cornell University that showed that workers experience an average of 2% increase in productivity with optimized lighting. So I know that many, if not everybody here, is very familiar with smart window technology. And when this project was initially pitched to me, I immediately was sold. I thought this was a great idea. But then I took a step back and asked myself, why do we not see these windows everywhere? And over the past few years, we've come to learn that there's a few drawbacks. So specifically, the most commonly explored electrochromic material is tungsten oxide, which is a great material, by the way. But unfortunately, tungsten oxide will turn blue in its colored state, and most users want something that's more color neutral or a black look. Additionally, these windows tend to switch on a more longer scale, sometimes on the order of minutes, potentially even tens of minutes. Also, the windows tend to cost a little too much, usually $50 to $100 per square foot, sometimes more. And we found throughout the years that the benchmark price, if we really want to make this technology explode, is somewhere on the order of about $20 per square foot. And one last thing is that these windows have usually a difficult time getting dark enough to be used for privacy applications, which would really allow us to implement them into the residential market. So if we wanted to design the ideal dynamic window, it would be something that could switch fast with color-neutral tinting. It could be cheap. It could be able to get dark enough for privacy applications, in addition to also being large and durable enough to last 20, 30, 40 years in real-world fenestration applications. Now, don't get me wrong. There are technologies out there that can do these things, but we really yet to see one technology being able to simultaneously achieve all of these. So in our group, rather than trying to fine-tweak existing technologies that people have been trying to optimize for the last few decades, we thought to ourselves, what would be the perfect electrochromic material? It would be something that would be able to block light extremely well. And we thought to ourselves, and the conclusion became clear, we decided to use metals. So our dynamic windows operate by the reversible electrodeposition of metals. So if you take a look at the diagram here at the right, essentially what we have here is we have metal ions dissolved in some type of solvent. We commonly refer to this as the electrolyte. Now, if we apply a cathodic potential to some transparent electrode, this transparent electrode is commonly a transparent conducting oxide, commonly referred to as a TCO. So if we apply a cathodic potential to this TCO, we're able to reduce these metal ions in the electrolyte onto the transparent surface, and this will induce optical tinting from a transparent to a dark state. Now, by simply reversing the polarity of this system, we're able to reoxidize this metallic film back into the electrolyte, and it will thus return to its initial transparency. So again, metals were such attractive choices to us because they have fantastic light attenuation properties. It's really estimated that you only need about 20 to 30 nanometers of a completely conformal, smooth metallic film to substantially block out a lot of light. Additionally, metals are rather stable, especially towards UV. Another great benefit is that metals can be very easily solvated and electrodeposited in what we call green solvents, something along the lines of water. And lastly, if you take a look at just the diagram here, if we want to look at just an initial cost benefit, everything here can be solution processed. And also, our main electrochromic mechanism here is from the electrolyte. So we're able to avoid any potential expensive sputtering layers that you commonly see with traditional electrochromic technologies. So since the electrolyte is the main source of what's actually causing our optical tinting, that's of course where we wanted to start our research and we wanted to focus on. So after many trials and tribulations, basically running through the entire periodic table of every metal, we eventually concluded that the reversible electrodeposition of bismuth and copper is where we wanted to go. So if you take a look at the devices here on the right, the reason that this bimetallic system was so attractive for us is that we're able to produce a black, color-neutral absorbing film, which if you think, and if you look at it at first glance, it's kind of surprising because when you think of metals, metals tend to be very reflective. But there's some really cool chemistry involved here that allows this bimetallic system to appear black and more absorbing rather than reflecting. So we're able to achieve a color-neutral tinting across the entire visible spectrum within 30 seconds and switch back to its initial transparency in less than 5 seconds. And we're able to do this cycling over hundreds of times. Now, I can talk your ears off all day and really nerd out about this to you all day, but I always felt that a video always does more justice than words. So here we have a video of one of our initial prototypes switching at an accelerated rate. So I'll let you take a look at this. So as you can see here, these windows are able to go from a nice transparent to a color-neutral gray, all the way to a very dark black state, and return to its initial transparency in a rather short amount of time. Now, I know what some of you may be thinking. All right, we have something that can switch fast with color-neutral tinting and some other great properties as well. One thing I wanted to mention as well is that there's some additional benefits to using metals for electrochromic applications. Specifically, we have a much wider optical range that we can work with compared to to other technologies for electrochromics. What I mean by that is that if we just keep plating more and more metal on the TCO surface, the window will continue to get darker and darker. Specifically, we're able, within 3 minutes, to get below 0.1% transmission, which is usually the numerical value associated with trying to reach privacy applications. So we could have potential applications in residential markets. And also, since my time being here in Finland, you all were not kidding about the midnight sun. So this also could be very useful for sleeping purposes in Scandinavia, especially in the summer. One also added benefit about this metal-metal architecture that we're working with is that we are able to switch this window into its complete private state, unplug the device, and it can maintain its opacity for as long as you need. So it's bistable in both its transparent and its private state. Now, I know what many of you are probably thinking. These are some great amenities to this technology, but this is all done on a 5 by 5 centimeter squared scale. And unless we're trying to make these windows for birdhouses, or in the words of Ben Stiller from Zoolander, trying to make a building for ants, it's really not going to be very useful. So there's a common issue when trying to scale this technology. Specifically, metal nucleation on these TCO surfaces is extremely poor. So the most commonly used TCO for these applications is a mixed metal oxide. It's actually a tin-doped indium oxide, commonly referred to as ITO. And ITO has some very interesting heterogeneous surface chemistries that cause metal nucleation to be very poor. Now, some of you may be thinking this actually is really not that big of a deal, but it becomes substantial when you try to scale this technology. The reason is that when you apply a potential to the edge of a TCO, you have current rolling through this material. And if you think about Ohm's law, if you have current running through a resistive material, you're going to experience a type of voltage drop. So we have a voltage drop here in this TCO from the edge to the center. If you combine this voltage drop with the poor metal nucleation properties of ITO, it will cause metal to preferentially plate on the edges rather than on the center. So when we try to scale this up to 100 centimeters squared, you can see that we aren't able to achieve uniform tinting. So this is completely not going to work for any type of real-world fenestration applications. So in our group, we had to think, how can we improve the metal nucleation qualities of this TCO? And the way that we went about modifying these electrodes is with platinum nanoparticles. So these nanoparticles are about 3 nanometers in diameter, and they're adhered to the surface through a self-assembled monolayer of thiol molecules. So if you take a look at the SEM images here on the left, we have our bare ITO surface, and you can see all the grains throughout out the TCO. And if you take a look, our platinum-modified ITO, you can see these light little white dots slightly just decorating the surface. These are our platinum nanoparticles. So we don't have a complete conformal film of platinum, so we're really not using much material. Additionally, this platinum modification does not change the transmissivity of the TCO, and it also does not affect the sheet resistance, which is great. So keep in mind what we were trying to prove. We want these platinum nanoparticles to improve the metal nucleation on our TCO. So the way that we went about testing this is we ran 3 electrode half-cell experiments on a bare ITO and a platinum-modified ITO surface. So for you electrochemists out there, we ran some cyclic voltammograms on this, and you can see when we introduce the platinum to this TCO surface, you can actually see that the onset potential for metal nucleation shifts about 70 millivolts. And that's exactly what we wanted to show. So what we're showing here is that the overpotential for metal nucleation is now lessened with this platinum modification. So platinum provides a much better surface for metal to nucleate compared to our normal ITO. Now I get it, some of you may be thinking that 70 millivolts, it's really not that much. But it's substantial because it changes the mechanism by which metal is now limited and which the nucleation is limited. What I mean by that is that there was this great study done by a colleague in my group, Michael Strand. And what he did was he showed that in a 3-electrode half-cell experiment, if you take a bare ITO surface in our bismuth copper electrolyte, and you vary the potential applied to this electrode, you can see that as the potential is dropping, the contrast ratio is also continuing to decay, which is exactly what we saw in our large-scale window where metal is only preferentially plating on the side. However, if you incorporate the platinum nanoparticles to this ITO surface, you can see that the contrast ratio remains relatively constant despite the voltage drop. And this is important because now the metal nucleation is no longer limited by the electrode's potential, but now it's limited by the diffusion of ions, simply the rate at which the ions can reach the surface. So when we want to translate this from a 3-electrode half-cell into an actual 2-electrode device, you can see that where we failed initially on a bare ITO surface to plate uniformly, now with the platinum modification, we're able to switch uniformly on a 100 centimeter squared scale. Okay, so now that we've tackled both the working electrode and the electrolyte, it only kind of makes sense to tackle the entire electrochemical cell. So we wanted to look at potential counter-electrode materials. So one great thing about this metal system is that it's compatible with ion intercalation materials, commonly found in batteries or other electrochromic technologies. So what we have here is that this material on the counter electrode will usually intercalate ions such as lithium, which is great because there's already a high concentration of lithium in our electrolyte, which was initially there for ionic conductivity purposes. So we had a wide range of potential materials that we could have worked with. And after many trials, we eventually stumbled on, surprisingly, one of the most commonly pursued electrochromic counter-electrode materials, which is nickel oxide. And nickel oxide was an attractive candidate for us because it's anotically coloring, meaning that it colors at opposite potentials at which our metal deposition takes place. So what we have here in the system is we can actually have both electrodes color at the same time. So we can establish a dual coloring dynamic electrochromic technology. So in collaboration with the Barile group at the University of Nevada in Reno, we were able to develop these hybrid dynamic windows that can switch from transparent to a color-neutral black in a few minutes over a few thousand cycles. One added benefit that we were able to show with this technology is its potential for flexible applications by relying on ITO and PET substrates. So now that we have the entire electrochemical cell stack figured out, our group has been very serious about trying to transition this technology from an academic setting to one of a more commercial or industrial scale. And the two things we put a lot of effort towards recently have been the durability and the scale. So on the durability end side of things, we wanted to identify any potential degradation with this existing stack that we have. And of course, as researchers, we want to rectify them as soon as possible. So what we noticed is that the acidic halide electrolyte that contains our bismuth copper system will actually start to slowly etch away the ITO surface over the course of a month. And we were able to notice this on the far left. I don't know how to use a laser. It doesn't work. You can see on the far left, we would note a slow rise in sheet resistance of the ITO electrode over the course of a month. And this will eventually cause the window to switch non-uniformly and eventually stop working entirely over long periods of time. We were able to rectify this problem by switching to a non-halide-based electrolyte, specifically ones that rely on perchlorate ions. So you can see here, when we use this non-halide electrolyte, we see no change in the sheet resistance over the course of a month. And this proves that our non-halide electrolyte is not etching the ITO surface. And this has been shown both experimentally in our lab as well as in previous academic literature. One added benefit with this new electrolyte is that in addition to being stable over thousands of cycles, we're not as limited with the metal solubility as we were in our previous halide-based electrolyte. What I mean by that is we're able to dump a ton more metals into our electrolyte to drastically increase the concentration of our system. This is very important and very useful because now we're able to achieve a much wider optical range in a much shorter amount of time. Specifically, here's just one example of being able to tune this electrolytic system where we're able to achieve less than 1% transmission in actually less than a minute. So in addition to tackling all the durability issues, we also wanted to focus on scale. So on the scale end of things, we wanted to develop an electrode that can minimize this voltage drop that I was referring to earlier. And the most common pursuit to try to minimize this is to try to create a TCO with much higher conductivity or much lower sheet resistance. And unfortunately, researchers have been trying to do this for decades, and ITO is kind of getting close to its limit in terms of how conductive it can truly be. So rather than trying to make a TCO with a much lower sheet resistance, we approach this problem from a different angle, specifically by trying to develop, not trying, but actually developing what we call a triple layer electrode. So this triple layer electrode essentially has our two normal TCOs with a very resistive inner layer. And what happens here is that when we apply a potential to our bottom TCO, since this material is much more conductive than the one above it, current will preferentially flow laterally rather than transversely, just by the idea of, current wants to flow through the path of least resistance. So by tuning the material's properties of these three layers, by applying a potential to our bottom TCO, we are able to drop a significant amount of voltage through our resistive inner layer. So even though our bottom TCO is still experiencing a significant voltage drop, we can now drop a lot of this voltage through the inner layer such that our top TCO, which is the layer that's actually exposed to the electrolyte within our window, only experiences a minimal voltage drop of about 0.3 or 0.4, which is the voltage tolerance that's needed to switch uniformly for our windows. And this will allow us to start switching uniformly on a foot scale, and we can further tune these properties to even reach up to a meter squared scale. So in addition to tackling the durability and scale issues associated with this technology, we have a couple other active projects to try to get a realistic understanding of potentially implementing this technology worldwide. So these include, one is that our lab recently moved to Boulder, Colorado about a year ago. And we're doing some elevated temperature and humidity testing, in addition to also testing our electrolytes and our seals under one sun illumination. And what's great about being located in Boulder is that we're only about 40 minutes away from the National Renewable Energy Lab, commonly referred to as NREL, in Golden, Colorado. And this is the facility in the United States that runs all the ASTM testing for dynamic windows. So we're in the midst of taking our windows and actually putting them in their testing chambers to test them at elevated extreme weathering conditions. Other things that we're actively pursuing is we're working to develop a durable counter electrode by a scalable, cheap process, something like spray coating. And then one last thing we're working on is that we're developing an electrolyte that is a polymer gel, or potentially incorporating a polymer separator in the electrolyte. This will be very important because when you have, I'm sure many of you are aware, when you have a vertically positioned window with a liquid electrolyte in there, you're going to have a massive hydrostatic head pressure build up at the bottom. So being able to do something that is more of a gel will help prevent any type of breakage of our seals. So kind of to wrap up everything that I've talked about here, what we have here is we have a technology that can switch from transparent to very dark, black, opaque, in under a minute. And everything here is made from cheap solution process techniques and materials. Additionally, these windows are able to get dark enough to be used for privacy applications as well. Now, one thing I love about this project, and I've really enjoyed working on it, is that there are many applications for this beyond just large-scale windows. I've listed a few examples we have right here. Some of these include tunable sunglasses or tunable visors, potentially tunable ski goggles. Also, they could be potentially used in display applications where you want a background that can go from something transparent to black. Additionally, they could also be used for adjustable shutters and cameras, and they could also be used for IR modulation for military or space applications. So having a background more in the science and engineering side, I would love the opportunity to meet and talk with people that have more of a background on the glass and windows, which seems like almost everybody here. So after this talk, I would love to meet with anybody about this. And I have to thank a lot of people because I wouldn't be here today without them, specifically my PI, Mike McGee. I would also like to thank our collaborator and former postdoc, Chris Barile, and the rest of my research team, both past and present, who I've had the pleasure of working with for the past few years. Additionally, I have to thank the funding agencies, specifically the Department of Energy, the Stanford Precourt Institute, and also the National Science Foundation for supporting this project. And finally, I'd like to thank everybody here at GPD, especially those who have helped coordinate and organize this event. This is my first time to Finland, and it's been a wonderful experience so far, and I've very much enjoyed it. And with that, I'd be very happy to take any questions that you may have.
Thank you, Tyler, for a very convincing presentation. Are there questions?
Hi, I was wondering by chance if it is controllable the shade you get. Does it go all the way from transparent to dark and nothing in between?
Right, so we're able to achieve intermediate transmissive states. But to actually hold something with no potential, right now we're only able to achieve it in a private and a transparent state with no power. But we're still able to achieve those intermediate states, but you're going to need to apply a little bit of power to maintain that state.
In research on thin film batteries, both in companies at universities, you see a trend actually in moving away from liquid electrolytes to solid electrolytes for safety purposes. Do you think safety will be an issue here as well if you use liquid electrolytes?
Right, great question. Now, in addition to safety, but also I was mentioning the issue of hydrostatic head with a liquid in a vertically positioned window. So that's what we're making serious efforts right now to create a cross-linked potentially cross-linked gel, something that is not free-flowing but can stand, something more along the lines of solid state. That's something we're actively pursuing, correct?
Okay. And if you do your aging test, do you also see metal nanoparticles coming off every now and then, moving into the liquid electrolyte? Or are they solidly stuck actually to your metal layer?
Right, great question. So when we introduce these platinum nanoparticles to the TCO surface, we actually have to bind them through a self-assembled monolayer of thiol molecules. So without those thiol molecules, the nanoparticles will eventually fall off. But having this adhesion, and there's cool chemistry involved there, will allow those nanoparticles to stay on. But we're starting to test them at elevated temperatures just to ensure they can last through the extreme weather.
Okay, thank you.
Mm-hmm.
As far as I know, ITO seems to really dislike DC current, tends to color over time, and so your transparent state would get browner. Has the platinum resolved that issue, or is it still something you guys have to work on?
Yeah, great question. So the browning of an ITO surface is usually caused by if you apply extreme cathodic potentials. It's usually caused by the reduction of indium and tin out of the substrate. So our system, we're operating less than a volt. So we're not actually working in those cathodic potentials where we can see any type of ITO degradation.
Other questions? Perhaps I have one question.
Yeah.
You said it's also for privacy application, but does it also work if you have a strong inside light and it's dark outside? Is it still then completely blocking?
I haven't tested it specifically coming from in and out, but yeah, either way you look through the window, it's completely, blocks out all of light.
Yeah, okay. Yeah. I can imagine on a sunny day if you cannot look in, but on a dark night, perhaps you can look in if there's a strong light behind it. But
True, that is something that we'll definitely be looking into. Yeah.
Okay, thank you very much again.
Thank you.
Hi there. Did you like what you just saw? If you did, why don't you like the video, drop us a comment below, and share the video as well, since GPD is all about sharing. And to receive more videos in future, subscribe to this channel and don't forget to click the bell icon. Ciao!